All right, Honors Chemistry, this is part 2 of the answers video for Lesson 18 on Solution Stoichiometry. We're going to go ahead and start here with part 3. These are A-B problems, meaning that the two problems, 1A and 1B, are identical. Virtually all the words are identical, except the only thing that's different is numbers. I'm going to do the A problem on each of these. Now, these are more difficult problems, so I want you to kind of study these. Maybe even take the practice problem, do it a second time or even a third time on a piece of scratch paper until you can do it perfectly, and then try doing the B problem. And that will reinforce it. So these are going to be a little more challenging stoichiometry problems here, okay? So let's get started. So seawater has a density of 1.027 grams per milliliter and is comprised mainly of sodium chloride and water. What is the molarity of a solution that is 3.5 mass percent sodium chloride? Okay, there's a lot to unwrap here and a lot of things that you haven't seen before. So let's go over what those are. First of all, you have to know the chemical compound by the name, okay? And that sodium chloride is going to be NaCl. All right, and the molar mass of sodium chloride is 58.44 grams per mole. You're going to need that in the problem. So remember, this is the short way of writing that, okay? All right, now let's go back here. It's seawater, and it has a density. Density is in grams per milliliter. It's in some unit of mass over some unit of volume. So what we want to do is write that in the expanded form, because that's what you're used to seeing this. So you need to know how to convert this, and that's why I gave you those exercises at the beginning of this particular lesson. So the way you would write that is you have 1.027 grams of solution for every, or which equals 1 milliliter of solution. So what a density does is it relates a mass, basically how much something weighs, to a volume, how much space it takes up. The classic one that we have is for water only, and I'll go ahead and write it up here because you're going to need it later on. This is only true of water, and this was actually, the whole concept was defined around the density of water, is that there is 1 gram of H2O equals exactly 1 milliliter. So exactly 1 gram equals exactly 1 milliliter. That's only true for water, okay? Now this is not water. This is a solution that is water, mostly water, but it's mixed with NaCl. So you'll notice it's a little bit more than 1 gram per milliliter, and that's because sodium chloride has a molar mass that's greater than water. Water is 18.02. Sodium chloride is 58.44, so if you mix in a little bit of sodium chloride, it's going to weigh more per milliliter than water will. Water will be exactly 1 to 1. Okay, so now you have these two parts here that you can make a ratio out of somewhere as we do this problem. You can create your ratio to do the stoichiometry. Okay, so let's keep going. So we've gotten through all of this. Now, what is the molarity? So this is what the question is asking for, molarity of a solution that is 3.5 mass percent sodium chloride. And this is a tricky one. Pretty much nobody understands what to do with that mass percent until you're shown. So I'm just going to show you how to deal with that. Okay? So there's several things that add complications to this. But fundamentally, it's a stoichiometry problem. And what we're trying to find is molarity. So what we're going to do way over here is we're looking for molarity. So what does that equal? It's capital M, but you never write it that way. You write it based on the units that make it up. So it's moles of your solute, that's NaCl, over liters of your solution, and that's NaCl plus the water mixed together. So that's what you ultimately want to get. You want to get moles of NaCl on the top and liters of solution, which is H2O plus NaCl, the whole thing mixed together, on the bottom. Okay, so what do you start with? What you're going to start with here is you have two numbers. We're going to start with mass percent, and it's just experience that'll tell you that that's the one and not the density. The density is going to be a conversion factor, as you'll see. But how do you deal with mass percent? So let's go up here, and I'm just going to sector off a little section. What is mass percent? It's grams of solute over grams of solution. So in this problem, the solute is NaCl, and then it's times 100%. So it doesn't tell you how much NaCl and water you're going to use. It just tells you it has to be 3.5 mass percent. That means for every 100 grams of water, you need to have 3.5 grams. Well, actually, for every 100 grams of solution, the two mixed together, water and the NaCl, you need to have 3.5 grams of NaCl. So what we're going to do in this problem, you get to pick how much you want to use, and you're going to choose 100 grams. So we're going to make this number on the bottom 100 grams. That means the number on the top is going to be 3.5 grams. That would be 3.5 mass percent. If this is 3.5 and this is 100, that is 3.5 mass percent. You could have picked other numbers. You could have picked 350 up here and 10,000 down here. Anything that's a ratio of 3.5 to 100. 3.5 to 100 would fit. But let's take the easiest combination we can think of. 3.5 grams on top, 100 grams on the bottom. So that's what we're going to say. We're going to say that 3.50 mass percent is 3.5 grams of the solute over 100 grams of the solution, SOLN, water and NaCl. So convince yourself that what I just wrote there does equal 3.5 mass percent. Okay, that's 3.5 of that. All right? So now we actually have some quantities in grams that we can work with. So just remember, whenever it's mass percent, you get to make up how much you want to use. You get to choose how much you want to use. And you're going to choose to have 100 grams of solution, and whatever that percent number is, that's how much of the solute you're going to have. Okay? So that's the first step here. Okay, so now let's take a look at the problem. Remember, we break it into two problems, the top part of the problem and the bottom part of the problem. All right, so the top part is we need to go from grams of NaCl to moles of NaCl. And we know that the molar mass, you get that off your periodic table by adding Na plus Cl. You know it's 58.44. So I'm going to go ahead and write that down here. Okay, that's your molar mass conversion right there. So is that. But this, we wrote it out in expanded form. That's why I wanted you to practice doing this, going from this to this. Okay, so now one of these goes on top here and one goes on bottom. Which one is it? I'm not going to draw the boxes because in these problems you're not always sure how many conversions you're going to have. It's not quite as cut and dried as it was in some of our earlier problems. But we know we're going to have one to go from grams to moles, so we have to have grams on the bottom. If grams is on the top here, it has to be on the bottom of our first conversion, so that's going to be the 58.44. And we have 1 mole on the top. There it is, okay? So we see you did that because grams of NaCl needs to cancel with grams of NaCl. Now you have moles of NaCl on the top, and that's what you want in your final unit. So we're done taking care of the top. The top is all done. We don't need to do anything else to the top. So now we're ready to start down here on the bottom, and we need to get from 100 grams of solution to liters of solution, okay? All right. Okay, so you need to be able to have some relationship between grams and liters of solution. And where do we find that relationship? That's the density right here. It relates grams of solution to milliliters of solution. Okay, but milliliter, we're going to make that conversion from milliliters to liters right after we do this. So understand, if it's water, it's easy. It's 1 gram, 1 milliliter. But this is not pure water. It's a mixture. It has some sodium chloride. That's a little bit heavier than water. So therefore, the number of grams per milliliter is going to be a little bit more than the number of grams per milliliter of water. But we're not interested in water right now. We're interested in this solution. There it is. So we need grams to cancel out and liters to appear on the bottom. Well, this isn't liters, but it's close. So we're going to go ahead and use this, and we're going to multiply 1.027 grams of solution over 1 milliliter of solution. Okay, so grams of solution cancels with grams of solution. And now what we have down here is milliliters of solution, and we need to get to liters of solution. Okay, and we've done this conversion several times already in this assignment. We know that 1 milliliter of anything, 1 liter of anything, correct that, 1 liter of anything equals 1,000 milliliters. That's true of any substance. But you always want to be sure you state what not only the unit of measure, but what the substance is, so you don't cancel the wrong thing. Okay, so we come up here. This is milliliters. We need liters on the bottom, so we put the 1,000 milliliters on the top. And specifically, it's 1,000 milliliters of solution. In this case, for every 1 liter of solution. Milliliter solution, milliliter solution. The only thing we have left down there is liters of solution right there. So our top units of measure are correct, our bottom units of measure are correct. And so now you just simply do the calculation. And what you get is 0.615 moles of NaCl for liters of solution. But again, the way we usually write an answer if it's molarity is 0.615 capital M, molar. Okay. All right, and the correct number of significant figures, we can do 3 significant figures because of that, so we're good on that. Okay, so what I do is study this problem. Be sure you understand the 3 things that are really new is how did you deal with that density? You turned it into a conversion factor of grams of whatever the solution is, in this case NaCl plus water, equals 1 milliliter of solution. That's what the density is telling you. It's telling you that relationship, so you can convert from grams over here ultimately to liters over here. The other thing you had to know is NaCl, okay, that's by name sodium chloride, so that's the molar mass for that, and you know how to deal with molar mass conversions by now. And finally, you had to know that 3.5 mass percent, and this is a key. Whenever you see that, you're going to convert that into that number of grams over that number of grams of solute over that number of grams of solution. So that is 3.5. In other words, you get to choose how much you want to use. And we're going to choose to use 100 grams of the solution. So therefore, we're going to need that's going to be 3.5 grams of the solute. All right? Okay, so a little to unpack. So practice this problem. I would practice this problem once and then go down to this problem. It's exactly the same. Now, I don't guarantee these answers are right, so watch this video rather than trust these answers. They may not be right. I may have changed the problem and not changed the answer. So be careful on that. Anyway, practice this once and then come down and see if you can do this one without looking at it. But peek back here if you need it, because these 2 problems are the same. All right? Okay, let's keep going. We are now going to go to problem 2A. And that's going to be the same as 2B. So what is the molality of lead ions in a solution that is 400 parts per million lead ions? So what does 400 parts per million mean? It means if you have 400 grams of lead, that's PB is the abbreviation for lead, you're going to have 1 million grams of the solution. That's the PB plus the water mixed together. We're always assuming that the solvent, always assuming the solvent is water, if it doesn't say otherwise. Okay, so what we're going to do is this. I'm going to do a little calculation here that you may or may not have to do in the problem. Well, I tell you what, I'll save it for when it comes up. Otherwise, it won't make sense right now. What is the molality? So molality, you look back on your reference sheet, and this is in the reference sheet section under concentrations. It's moles of solute, the same as molarity on the top, over, this time the bottom's different, it's kilograms of solvent, and the solvent in this case is the water. So you can write either the word solvent, or in this case, in almost every case, it's going to be water, so you can go ahead and write that. So what we want to get to at the end is these two right here, okay? All right, now, what are we starting with? Well, we're starting with this, that you have 400 grams of lead for every million grams of solution. So we're going to put that way over here. And again, on these problems, I would use every bit of space that you can, okay? Okay, so let's look at what we have to do. We have to get from grams of lead to moles of, and I can just go ahead and write it here, moles of lead. That is the solute. Okay, so that's easy. That's a molar mass conversion. So let's go ahead and write down the molar mass for lead. Okay, and the molar mass for lead, there it is, PB, it's 207.2. Okay, so 1 mole. Okay, there's the molar mass. So we're going to go ahead and do that right away to convert from grams of lead to moles of lead. So grams has to go on the bottom because it needs to cancel. And it's going to be 1 mole on the top. Grams of PB cancels. So now you have moles of PB. That's your final unit on the top. So that one was pretty easy. All right, now this one's more challenging. You got to make 2 conversions here. One is from grams to kilograms, and one is from solution as your substance to water, the solvent. And you're going to find that we can do something a little bit unusual with the unit, with the cancellations that we've never done before. Okay, so let's go ahead and do that. Okay, so the first thing we're going to do is convert from grams to kilograms. So you need to know the relationship. Kilo means 1,000. So this relation is 1,000 grams, and just like liters to milliliters, it's of any substance. It doesn't matter what the substance is. So 1,000 grams equals 1 kilogram. Generally, kilograms is the unit you use in physics class, whereas grams is the unit we use in chemistry. Okay, it's just physics usually deals with bigger objects, whereas chemistry deals with small amounts like this. Okay, so in this case, we're going to use this conversion to get us from grams to kilograms. Now, something funny is going to happen here. We're going to go from grams of solution. So we have 1,000 grams, and it's going to be of solution. To 1 kilogram of solution. Okay. So here, grams of solution cancels with grams of solution. And now on the bottom we have kilograms of solution, but we need kilograms of H2O. So we've got the right unit of measure. Let me get rid of this because I need all the space I can get here. We've got the right unit of measure, kilograms, but the wrong substance, solutions and H2O. So now we need a relationship between the solution and the H2O. So what you have to remember is this. I'm going to write it right here. The solution is equal to the solute plus the solvent in grams. Okay, the solute is the lead and the solvent is the H2O. So what that means, if I put numbers to that, the solution we said we have 1,000,000 grams. And the solute is the lead, we said we have 400 grams. So that means since we know we have 1,000,000 and 400, then the solvent is going to be whatever adds to 400 to give you 1,000,000. So this is what we're figuring. So another way is you say 1,000,000 minus 400 to get the solvent. This is grams of solvent. Remember, that's the H2O. Okay? And that's going to be 999,600. Okay? So that's how many grams of solvent we have, H2O. Okay, this is grams of solute, and this is grams of solution. So solution equals solute plus solvent. Okay, so we worked backwards to figure out what our solvent is. So now we know how many grams of solvent we have. So for every 1 million grams of solution, we have 999,600 grams of H2O. Now we're going to convert both of these to kilograms because everything's in kilograms here, all right? So you do that by dividing by 1,000. I'm not going to work it out longhand, okay? Just it's divided by 1,000. It's the same conversion. I'm just not going to write it out here, okay? So that means 1 million grams is 1,000 kilograms of solution. Equals, this is 400, so we're not worried about that. This is grams of solvent, and in kilograms, that's 999.6 kilograms of solvent, of H2O. Okay, so we have a relationship between, for every 1,000 kilograms of solution, we have 999.6 kilograms of H2O. So now we can come down here and write that. Kilograms of solution has to go on the top. That's 1,000. And kilograms of solvent has to go on the bottom, and the solvent is the H2O. Okay, so kilograms of solution cancels with kilograms of solution, yeah? And you have kilograms of H2O on the bottom. So you've set everything up completely, all right? So I'm going to draw an arrow there like that because we need to put our answer down here. We don't have enough space. So now it's going to be 400 times 1 times 1,000 times 1,000 divided by a million divided by 207.2 divided by 1 divided by 999. Let's go ahead and do that. All right, and when we do that calculation, we get 0.00193 moles of PB per kilogram of H2O, and we call that molality, so it's small m. So that's your final answer, okay? 0.00193. Okay, that's how you do that. So this one is the same as this one. This might be the hardest problem. A lot of tricks there. How did you get, how do you get from solution to solvent? And you have to see that there's that relationship. Okay, so I'm going to wrap up this video right now, and I'll continue it on the next video. There's going to be several videos to this problem set. Okay, these are some of the most complicated problems that you'll do in this class. So I want you to, again, that's why I'm doing an A-B format where the B problem is exactly like the A problem. I want you to practice the A problems and then do the B problems. I'll continue this on the next video, and so I will see you in class.